Hello, everybody. I feel like it's been forever since I've done a note party, so let's get back after it, right? Okay. So we just kind of finished up chapter 10, so we're moving on to chapter 11. And chapter 11 is volume of three-dimensional figures, okay? Now, a term that is used for three-dimensional figures is prisms. And prisms are three-dimensional figures whose bases are parallel and congruent. Now, this is very important to understand about prisms. They are parallel and congruent. So remember what parallel means. Parallel means they are in the same plane but never intersect. Okay, we talked about parallel lines for a very long time, but these are now shapes. Okay, they're parallel. So shapes are parallel and they're congruent. Remember, and congruent means the same shape and size. Same shape and size. Okay. All right. So, what again? The most common misconception about bases are what the figure sits on, and that is not the case when it comes to prisms. And let me explain. So, for example, a triangular prism. The most common triangular prism that I think I can explain to you would be a tent. And a tent looks, something like this. This is kind of like your triangular part you go in, and then this goes out. All right, so this is a triangular prism. Now, understand why it is a triangular prism. Based on the definition, remember the bases are parallel and congruent. Well, this triangle and this triangle are parallel and congruent. Those are the only sides in this three-dimensional figure that are parallel and congruent. If you look at the other parts of the tent, and I'm calling it a tent, this part right here intersects this part right here along this line, or this part right here intersects this side over here at this line. Oops, sorry about that, guys. At this line. Or these two sides, this side and this side over here, they intersect at this top part right here. All right. So all of the other sides intersect, which means they're not parallel, which means they cannot be the base. Okay. So you name a shape based on its base. Okay. So this is a triangular prism because the bases are triangles. I'll draw one for you where, and again, remember the most common misconception is naming the prism based on um, the the shape of the base. But again, remember the most common misconception is thinking because the tent sits on this, everybody wants to call this the base of the tent, and it's not the base. So when it comes to prisms, bases are parallel and congruent, right? So the first thing you want to do when you get a three-dimensional figure is determine which sides are parallel and congruent. Then you know that those are the bases. Here's an example of a triangular prism that would be drawn where it looks like it's sitting on the triangles. Right? So this is like a base. So that's a triangular prism. Okay. All right. Then you have a rectangular prism, probably one of the most common ones because of a cereal box or something crazy. But there is a rectangular prism. These sides are parallel and congruent. They are rectangles, so that is a rectangular prism. All right. Now, don't be confused. These could also be the bases, right? These could be the bases because they are parallel and congruent. And the top and the bottom, I mean the sides, the front and the back could also be the bases because those are parallel and congruent. So when it comes to a rectangular prism, you have multiple choices to be your bases based on which rectangles you are picking to be the base. Okay. And then there is a square prism, which now if you think about it, the base is a square. So all of the sides are the same length, and we don't care how tall this goes, just as long as the base is a square. So if this side is the same length of this side, which is the same length of this side, which is the same length of that side, this is a square base. This is parallel and congruent, so this is a square prism. You can have any shape as the base. Those are the most common shapes that we use when it comes to um, three-dimensional. Okay, but there are others. If any of you are huge UFC fans, they talk about the octagon, right? And that's where the guys fight, essentially. But an octagon is a eight-sided figure. There's the eight-sided figure, and then of course, if all of the the fencing around the octagon, that is your. So that is it would be considered an octagonal prism. Okay, but again, we're going to deal with triangles, squares, and rectangles. All right, then the second one, the that's prisms. Then there are cylinders, and cylinders are like prisms, but the bases are circles. So here's a circle, and then here's a circle. That is now a cylinder. Cylinders do not have to go up and down, right? They could also lay on the side, like if you knocked over a can or something like that. They are cylinders, okay? All right. So those are the shapes that we're dealing with. All right, try to get that all in your mind and stuff. And what we're going to do today is we're just going to talk about finding the volume. And the volume is how much stuff you can fit in this three-dimensional figure. Um, the amount of cereal that is in the box, that's the volume of that cereal box, okay? All right, so here's the formulas for finding the volume of these prisms and cylinders. Volume is equal to capital B H, and you will hear me always refer to this as capital B H. And the reason why I want to specify capital B is because capital B has a specific meaning to it. Capital B stands for area of the base. Okay, now remember these prisms and cylinders, they have different shapes for their base, which means this formula, area of the base, will change. If you have a triangular prism, right? If you have a triangular prism, your capital B is equal to 1/2 base times height of the triangle. All right, so you got to focus on just the triangle. If you have a rectangular prism, right? If we have a rectangular prism, then my capital B becomes base times height, the base and the height of that rectangular base. Um, if we have a square prism, okay, if we have a square prism, since each side is S, your capital B becomes S squared. Or if we have a cylinder, because remember the base is a circle, the area of a circle, the capital B for this one would be pi r squared. Okay, so the capital B changes for each shape of the base. The capital B changes for each shape of the base. All right. Now the H stands for height of prism or cylinder. Okay, that's the height of the prism or the cylinder. In other words, okay, in other words, it is the distance between the bases. Okay, so the bases are parallel and congruent. So if you think about it, going back to this triangular prism I drew up here, since the triangles are the bases, then the distance between those triangles is the height of the cylinder or prism. That would be the height of that prism. If this rectangular prism, since these rectangles are the bases, then the height is the distance between them. This height is the distance between them. Since this square prism has these squares as bases, then the height of that square prism would be the distance between them. That's the height of that square prism. And the same thing with this cylinder. If this circle and this circle down here are my bases, then the height of the cylinder is the distance between those. This is the height. Okay. All right. So what I want you guys to do is I want you to take notes on this. I want you to watch this video at least 2 more times, please, to get an idea of really what's going on. And then when we come back, the next video I share with you guys will be me working out some of these problems of finding the volume of prisms and cylinders. All right, I hope everybody is doing well. I miss you guys, and I hope everybody is doing well, and I will chat later. Goodbye, everybody.